Hello and welcome to the CS4 interview. Joining me this week is Dr Nathaniel Virgo from the University of Tokyo. He's going to be talking about Gaia before life, autocatalysis and the prebiotic ecosystem. An intriguing title, Nathaniel. Welcome, thanks for coming. You do some very interesting research which we're going to talk about in a moment, but I wanted to first understand, how did you come to do the things that you do now? Because your undergraduate degree was in computer science, and then you did a master's in ecology or mathematical models in ecology. So that was a bit of a jump. So what happened in between you studying computing and then ending up working in theoretical ecology?
So I guess I just decided that I wanted to put my skills to use in something to do with the natural world at that point, and I thought, well, I had some quite good kind of technical computer skills and mathematical skills, and that perhaps modelling ecology would be a good route to go with that. Yeah.
I mean, had there been a long-standing interest in ecology, or was it?
Yeah, well, I mean, I'd always been interested in, during my computer science course, I was very interested in modelling evolution, and so I'd always had this kind of interest in evolutionary dynamics, and kind of taking that in the direction of kind of the natural world and contributing to our understanding of the Earth system was just something I was very interested in.
So this was theoretical ecology. So you weren't out like chasing butterflies or
No.
hunting tigers or anything. These were like doing maths.
Yeah. It was very much a maths, very much a kind of mathematics with its applications in theoretical ecology was really the focus.
Okay. And then there you ended up doing your PhD, or DPhil, your doctorate at the University of Sussex. So what was that about?
Well, yeah, I mean, that comes back to this long-standing interest in modelling evolution, which was the kind of main thing they did there. So I guess I went to Sussex with some crazy ideas of what I wanted to do, and ended up doing something completely and utterly different.
Okay, we're in the right place because Sussex at the time was a bit crazy. Yeah. So you ended up working, well, one of the things you looked at, I know, was non-equilibrium thermodynamics, which is a long-sounding thing for quite a potentially complicated thing. Are you able to give a pithy definition of what non-equilibrium thermodynamics is?
Yeah, so equilibrium thermodynamics is what we use to figure out what will eventually happen to things like chemical reactions. It basically says that a system will approach a state with the maximum entropy, which is just a number that you can calculate. And then non-equilibrium physics is really just the study of how a system will go from a state that doesn't have the highest entropy to the highest entropy state, trying to work out which route it will take. And it's very important because the things on the Earth are very far from equilibrium, particularly living things, and so non-equilibrium thermodynamics is a tool that we can use to help us think about that.
So you talk about living things, so I suppose they're classical non-equilibrium things, as things come in and the waste comes out, so there's kind of constantly driven systems which operate over energy gradients or something. So I guess I'm sure that people, certainly biologists for quite some time, have got that idea. But what about the idea of the biosphere being an open or non-equilibrium system? So that was some of the research you looked at in the Max Planck Institute, right?
Yeah, that's right. So, I mean, again, non-equilibrium thermodynamics is something that you can actually fairly straightforwardly apply to the Earth system as a whole, because although the individual living things on the surface of the Earth are extremely far from equilibrium, that makes them very difficult to model. The things that they eat and the gases that they give off and so on, those things have entropies that you can calculate. They're relatively close to equilibrium, and so you can use non-equilibrium thermodynamics to think about the Earth system.
Okay. So in thinking about the Earth system, presumably this got you thinking about the first word in your title, which is Gaia. So Gaia is this formulated by
Lovelock and Margulis
in the late 1960s, early 1970s. This notion that the planet is some kind of homeostatic or self-regulating, self-organising entity, and it's been somewhat misunderstood or misinterpreted. Let's say there's a relatively lunatic fringe who think the Earth is a living thing, or ideas of Mother Earth. But there's also the sensible science stuff, which obviously is what you look at, being a sensible scientist. Right. So, to what extent does the non-equilibrium nature of the Earth have important messages or input for looking at Earth in a kind of Gaian context?
Well, I think that's a very interesting question. So one of the results that you find from non-equilibrium thermodynamics, whether you apply it to life or not, is that things tend to reach steady states. Those steady states tend to have certain features, like matter tends to get cycled around in one way or another, and they can be more or less stable to perturbations. And so Gaia, in a way, is just an example of the sorts of things that can happen when an energy source is driving a system. So it's not really some kind of like mysterious thing that we don't understand. It's just that when you get non-equilibrium systems of that kind of complexity, perhaps what we might call homeostasis or self-regulation is the sort of thing that you should expect to see.
Because on the one hand, in a biological context, homeostasis is it's easy to understand conceptually. We might struggle mechanistically understanding all the kind of biomechanical, biomolecular processes which help us regulate temperature or pH in blood or whatever we regulate. But the idea that somehow a planet can do it, which is a very complicated thing, but also not a living thing, we haven't had populations of planets which have evolved. So the argument is that its fundamental non-equilibrium nature is one of the important reasons why we might expect it to be typically more homeostatic than not. Okay, so can you give me a simpler example though, because the planet's all big and complicated. What about something on a smaller spatial or temporal scale, which might be a simple physical system, but sort of it's a non-equilibrium system, but still displays some of these kind of homeostatic properties?
Yeah, so I think something, for example, like a hurricane, any kind of convection cell, but hurricanes are a nice sort of example. So that's a non-equilibrium system because the upper atmosphere is at a much lower temperature than the sea surface, and so what happens is that you get matter cycling, just like you do in ecosystems with the carbon cycle and so on. But in this case, it's a very straightforward physical motion, which just happens because of the moist air, the warm moist air at the bottom being heated more to go up to the top. And so, but a hurricane is kind of homeostatic. I mean, it's kind of hard to destroy it. It builds itself into this very complex physical structure, which is then quite stable. I mean, they dissipate eventually when they go over land, but as long as they have a nice warm ocean surface to be over, then they're very sort of stable systems, even though they're very far from equilibrium and very complex.
So that they've got stability in that they maintain their structure, but the things in which they're made of are constantly moving. So the hurricane, if it's moved 1,000 miles, there won't be any of the actual matter that was in it 1,000 miles ago, which kind of has the same feeling of living systems, where there's some kind of shared property, maybe some notions of information, but the things that you're actually made of, there seems to be a constant flux. So stuff comes in and the other stuff comes out. Okay, right. So in terms of this Gaian notion, right, so we've got this non-equilibrium system, which is kind of homeostatic, a bit like a hurricane, or in regions of, but to what extent is the role of life important in some notion of planetary homeostasis? Because you can imagine, I don't know, like Jupiter's red spot, that's kind of like a turbulent, dissipative process which seems to be quite robust. but there seems to be something special about the Earth because it's got all this life on it. So what's the role of life?
Well, I suppose the claim that I want to try and make in my talk today is that the role of life in the Earth system, or Gaia, is in a way opposite from what we normally think. So we normally think, well, you have life, and then that causes this self-organizing homeostatic Earth system to exist.
Mm-hmm.
Whereas what I want to say is that on the Earth we started with a homeostatic self-organizing Earth system that was presumably extremely different from the one we have today, but that life is actually a consequence of that on the Earth, or that life at least emerged in that context, and that these kind of self-regulatory processes were actually very important for maintaining the conditions that were needed for life to arise in the first place.
Okay, so if you're talking about the conditions under which abiogenesis may have occurred on Earth, I mean, we'll never know, but let's say you've got Mike Russell's white smokers, or Fax's white smokers idea, you know, the kind of chimneys and the hot soups, and these are kind of self-regulating. I mean, they can persist for quite some time. They seem to be moderately robust to changing environmental conditions. So the idea is that because we already had these sort of homeostatic mechanisms, they provided the conditions under which we may hope to see life form.
Yeah, so it's partly that, but it's also that you have to. So within the Earth system today, life plays an extremely important role. So it isn't just that we have this homeostatic thing and then that maintains the conditions for life, and life doesn't then have anything to do with it. It's actually the presence of life contributes back to this feedback. So the idea that I would like to present is that you have some kind of prebiotic thing, some kind of chemical system we call it autocatalysis, some kind of chemical system that's capable of growing in a similar way to the way that life grows, and kind of chemically affecting its environment in a similar way to the way that life does. Because that will eventually turn into life.
Mm-hmm.
Or that's the idea, that you started with something like that, and it eventually became life through one mechanism or another. And the idea is that once you have that sort of thing in the context of these feedback loops, this stabilizing feedback loops, that will maintain the conditions that are kind of good for this good for this growth thing, and actually maintain conditions that will make it more likely for it to be able to develop into more structured forms, eventually perhaps progress towards life.
Okay, so once life started, why wasn't it the case? Because, well, we can imagine life started on Earth, and let's just say it started once, or we'll only let it start once, and it can either participate in the kind of negative feedback loops which allowed it to exist in the first place, or gave rise to it, or it does something really, terribly destructive and just, wrecks the whole joint and the system collapses. So it's obviously not been that one, because we're here to ask the question. So are we just lucky to live on a planet in which life has been, us to be fortunate enough to live on a planet in which life has participated and maybe even promoted some of the homeostatic processes? Or is there something more fundamental that you're alluding to, that as soon as you get life going, it will more typically or almost inevitably stabilize these negative feedback loops?
Well, I mean, this is a pretty difficult question.
Yeah,
but I suppose the point is that typically what you see in non-living systems is that, I mean, maybe sometimes you do get things that appear that then wipe themselves out, but you never really see those.
Yeah.
Because they wipe themselves out. Whereas if you look at the world, the non-living world, you see things like hurricanes and great red spots on Jupiter and whatever else.
Mm-hmm.
So just the evidence is that, for reasons that may not be particularly easy to understand, but the evidence is that you do tend to get things that build up kind of very complicated positive feedback loops. And so life is essentially just, possibly, hypothetically, just an example of that sort of thing.
Okay, So you just said complicated, which is good, because it's the complex systems.
Yes.
So in conjunction with homeostasis, or you've got these self-regulating homeostatic processes, abiotic, so they could be geothermal, geochemical. These autocatalytic little molecules pop up and then start doing their thing. But really what we want in a story of the history of life on Earth, we want them to get more complicated. Right? We want them to get longer, we want them to avoid Huygens paradox, we want them to become the interesting life that we see and observe. So do these things necessarily go hand in hand? Do you have to have some kind of homeostatic property of the very early kind of the prebiotic ecosystem in order to get future complexity?
Yeah, I mean, I think that's in a way the really central point. So the idea is that if things are too easy, so you've kind of got three possibilities. You've got something that's kind of able to grow and reproduce itself in any sense. Then either the environment is too harsh and it just can't do it and it dies, or the environment is very easy, in which case it just that you'll just be lots of it, but it won't necessarily do anything very interesting. Whereas if it's kind of just right, then maybe it will grow to a point where it can't grow anymore, and then it's only by developing a new adaptation or changing in some way that it's then able to progress.
Mm-hmm.
And the idea is that the feedbacks, these kind of global feedbacks, or they need not be on the global scale. As you said, they could be on the scale of things like white smokers on the bottom of the sea, but they could easily be on the global scale.
Mm-hmm.
And that it's those feedbacks that kind of keep the conditions like just right, so that this thing is not too easy. It can't just spread. It can't just become a homogeneous slime that self-reproduces and covers the Earth.
Mm-hmm.
But it's not so hard that it's not too hard, so that it just all dies out. But it's somewhere in the middle, and that allows it to progress towards complexity.
Okay, so I can imagine there's the axis of being easy and then being hard. Are you able to give any kind of dimensions on that axis in terms of, let's say, Kepler's finding lots of different planets, exoplanets. Do you think there's any possibility of using some of your ideas at some point in the future when we can, let's say we can be able to do some spectral analysis of their atmospheres or something, or get some more information about the planets, that you would be able to say that's a good candidate, or maybe that's not such an interesting candidate?
Yeah, absolutely. So this was there's some work that I did at the Institute for Biospheric Theory and Modelling in Germany, and essentially you can, so detecting life or not life is extremely hard, but detecting a planet that's very far from thermodynamic equilibrium is certainly something that we should be able to do within at least the coming decades, maybe sooner,
Mm-hmm.
through spectroscopy. And so then it becomes a question of, well, is this planet far from equilibrium because it just happens to be stably far from equilibrium and there's not much happening there, it's just sitting there? Or is it far from equilibrium because there's something, maybe life, that's kind of very active?
Mm-hmm.
And so the tricky bit is that you have to know how fast things are happening. So it's not an easy thing. But I certainly think that within a few decades, if there are very far from equilibrium planets in other solar systems relatively nearby, we should be able to detect them. And then maybe it will be some time after that before we are able to say whether it's life or just something else that's really complicated.
Yeah, quite.
Yeah.
So that kind of harks back to Lovelock's early ideas when he was first proposing the Gaia hypothesis, and that it would be a biomarker or an indicator for life elsewhere. So he said you don't need to go to Mars, you just need to look at its telescope, and if your predictions of the Martian atmosphere, which you base on Martian geology, match your observations, then there might be life, but it's not going to be very interesting. So you're thinking of, essentially it's a kind of an update of that idea. So by which we might be able to detect at least candidates for, let's say, a vigorous or widespread biosphere. So do you think, let's say in 20 years, there are going to be any good candidates? What's your hunch? I suppose in answering that, how widespread do you think life is in the universe?
Well, I tend to think that it's probably very widespread. I mean, with the proviso that I'm not really sure exactly what life is, but if we talk about very complicated, far from equilibrium things that can kind of reproduce and evolve and that kind of thing without having to tie ourselves down to saying that is life or isn't. But I think that sort of thing is probably very widespread in the universe, because the ideas that we've been talking about kind of suggest that it's not so hard to kind of regulate a planet into this regime where this sort of thing's going to happen. So, so yeah, the idea is that it happens through regulation and not through coincidence. Although having said that, there's plenty of planets that we know of in our solar system where there isn't life, so we know it's not too easy either. But yeah, my suspicion is that it's not too hard, and so, although of course I don't know for sure, I'm actually fairly optimistic that we'll detect an exo-biosphere within the next few decades.
Okay, well, what about the solar system then? Because we can, okay, Venus, it all went wrong. Okay, so it's a horrible runaway greenhouse atmosphere, which is, bodes, behave yourself, Earthlings, this is what's going to happen to your planet. And Mars is too cold and small, let's say. But what about some of the, the satellites of, say, Saturn or something? What about some of the icy worlds? What about more exotic forms of life? Could you think there could be any in our own solar system other than the Earth?
Well, and it's certainly possible. I mean, the icy satellites are popular candidates. There isn't a huge source of energy on those worlds, but there is a source of energy from thermal frictional heating of the interiors. Another wild possibility would be Titan. So although temperatures on the surface of Titan are far too cold to find liquid water, there are liquid hydrocarbon lakes on the surface. And the interesting thing is there is an energy source on Titan, which is that the photochemistry in the atmosphere of Titan causes complex hydrocarbons to be formed, and these then presumably precipitate down onto the surface. And these molecules will contain energy. They're that type of molecule. There are bacteria on Earth which can extract their energy from that type of molecule. If it's possible for something like life to exist without liquid water, then it's possible it might exist on Titan. I mean, I don't want to say I think it does or anything, but it's there's a possibility.
Well, you might want to if you want to write a large grant to propose another mission. Okay, so these are all the really interesting questions that they're fascinating questions that people have been wondering about for as long as we've been wondering, I suppose. But you're using some very new tools in order to think about them, like simulation, computer models, right? So what's the role of, let's say, simulation in some of your work? Is it are you doing kind of analytical treatments? Are you doing little agent-based simulations? Do you have I've seen some of your work on, let's say, reaction diffusion systems. So is there a particular flavour to the kind of simulation activity that you do?
Yeah, I mean, typically I tend to be interested in general principles. So I'm interested in what's a simple system that I can set up that's kind of physically plausible. Doesn't necessarily represent any real chemicals chemical system that exists on the Earth. Although of course it's important to be kind of close to them, or in plausible range. Don't want to ignore reality. But the interesting thing is to try and set up systems that are simple enough to be maybe not analytically tractable, but simple enough to be understood, that can be simulated on the computer, that will then exhibit the sorts of phenomena that I've been talking about.
Okay. So these are quite conceptual model, but you are about to, or at least proposing to do, actual experiments, which is, I believe you're being expelled from the Society of Artificial Life for doing real-world science. So what's all that? You're going to be using real chemical systems to look at notions of water catalysis?
Yeah, that's right. So in the origins of life, there are a few famous experiments. One of those is the Miller-Urey experiment, so it's quite an early one from the 50s, where which again is very similar to what happens on Titan we were talking about earlier. So what they did there was they got a collection of gases that they thought would be the composition of the early atmosphere. Maybe it wasn't, but it doesn't really matter. And then you basically put electric sparks through that, and you generate all these very complex set of molecules, including things like amino acids. And then there's another way to create a similar set of molecules, and that's by taking hydrogen cyanide and just basically put it in water. And hydrogen cyanide molecules, they have a hydrogen and then a carbon and then a triple bond and then a nitrogen. That triple bond doesn't really like to be a triple bond, it prefers to be double and single bonds. So if you get a bunch of cyanide molecules together, they tend to swap electrons with each other and turn into these big complicated things. And that's probably one of the main mechanisms in the Miller-Urey experiment. But the problem is that although these experiments are very important and very impressive for the wide range of molecules they create and the fact that some of them are ultimately the building blocks of life, it doesn't produce life. It produces a black sticky tar which is made up of all these molecules just kind of jammed together at random. And so then the question is, well, how can you move on from that? How can you take that type of experiment but modify it so that something will happen beyond just getting tar? And so what we hypothesize is that if you, in addition to having these molecules building up in this experiment, you also have something that breaks them down, then maybe that can lead to autocatalysis, and I'll present a model that shows it's kind of plausible that it will. Autocatalysis just means something that can grow exponentially. And so it's kind of analogous to in a living cell you have anabolism and catabolism, which are words for the building up and breaking down of polymers. So yeah, the idea is that maybe these experiments just, what they're missing is the breaking down happening at the same time as the building up, and I mean it's early days, but we're aiming to try and make that happen in real chemistry.
Yeah, it's early days, and certainly over geological timescales, we're scrabbling around trying to see if we can produce conditions which would generate life. But do you think we just got the wrong mindset if we expect anything particularly interesting to happen over months or years? I mean, do we need millions of years to see something interesting? Or maybe the way I could ask you is, the origins of life, how quickly did that happen? At what point would you say, yeah, that thing looks like it's kind of alive, or at least it's a proto-life? Would it be a relatively quick thing? If it would have happened to your system, how long do you think you'd have to wait?
Well, I mean, I hope that it would happen within a few weeks at least in our system, because of the time it takes to perform experiments. I mean, so a few weeks is probably a minimum, because these polymerization reactions are quite slow. They take about a week just to do the polymerization, or a day just to do the polymerization. But yeah, so there's a school of thought that the origins of life must have taken a very long time because it took such a massive coincidence for like the first self-replicating molecule to form just from random coming together of atoms for no reason. So and then certainly it's possible that the origins of life required. I mean, some people think that it required such a big coincidence that the Earth could have easily never had life. It would have just sat there. Which to me has always seemed hard to imagine, because got all this energy available to be eaten, and then surely something somehow is going to come along and eat it. So there's that debate there, and I tend to be on the other side. I tend to think that actually because I think life arose through this kind of self-regulatory processes, rather than through this kind of massive coincidence forms the first cell scenario. I actually think maybe it could be something that could happen relatively quickly. Maybe so to actually get life, like complete with the DNA and the genetic code and everything. Obviously, a lot of those things are the product of evolution, which does take a long time. But to go from a completely inert chemical system to one that maybe has lots of self-reproducing complex molecules, maybe it's not so hard. Maybe it doesn't take such a long time.
I mean, it sounds fantastical to begin to imagine that you would actually have life forming your simple little reactor.
Again, I'm not really sure I'd want to call it life. I mean,
Proto-life, prebiotic, something that maybe over time will become life. But I suppose in a way it's just no more fantastical than, you've got a ball of rock orbiting a fusion reactor 90 million miles away, which, and life suddenly happened. So I'd be certainly very interested in you coming back, maybe not next week or whenever you actually get the initial results, and you can tell us all about it. But unfortunately we've run out of time, because now we have to actually listen to your talk. So thanks again for coming. You've done very well with the jet lag, and I look forward to your talk. Cheers.
Great. Thank you very much.